In this video, we're going to cover the wave equation and how to determine the speed of a wave on a string. The wave equation says that the speed of a wave is the wavelength of that wave times the frequency of that wave. You could also rewrite this knowing that the frequency is 1 over the time. You can make a substitution and say that it's the wavelength over the period. And I think this makes a lot of sense because the units of the wavelength are meters and the unit for the period is seconds, and so you're getting a speed in meters per second. It's not as obvious when you write it this way because the units of the wavelength are meters, but the units of frequency are hertz. But we have to remember that a hertz is equal to a 1 over seconds. So now if you multiply them, I think you can see meters times 1 over seconds, you're going to get meters per second. The thing that's you have to remember about this kind of stuff is that the constant in this equation is typically the speed, actually. And that might be surprising to some people, but the things that affect the speed of a wave have to do with the state of the medium. So for instance, in a water wave, the depth of the water will affect the speed of the wave. In the case of the waves on a string, we're going to find out that it's affected by the tension in the string and the mass per length of the string. In the case of sound waves speed is affected mostly by temperature. So these are the kind of things that can affect the speed, but for most given situations, the speed is a constant, and when the wavelength goes up, the frequency goes down. They become inverses of one another. Calculations involving this are actually pretty simple. You just have to make sure that you correctly identify your variables and you know the difference between a frequency and a period. Which brings me to the point is, how do you know the difference between a frequency and a period? Because sometimes you'll see a phrase that looks like this. A wave bobs up and down every 10 seconds. In another situation, you might say that 10 waves pass by a particular point per second. Now, my easy way of determining which one of these is a period and which one's a frequency, if you see the number immediately followed by the unit of time, this is a period. If you see the number and a whole bunch of stuff before you get to the unit of time, that's when you know you have a frequency. So for instance, one of the things that can be very confusing about frequencies is you might hear them a frequency referred to as waves per second, or cycles per second, or vibrations per second, or oscillations per second. There's a lot of different ways to describe repetitive motion. You can call it oscillations and cycles or orbits or any number of things. Even though there are a lot of different synonyms for waves, the big clue here is that they take their time getting from the 10 to the second. And that's how you know you have a frequency. Okay, another thing that we want to look at is waves on a string. This is the only calculation of a wave speed that we're going to actually do in this class, though there are other formulas for other types of waves. But if you have waves on a string, the formula for the speed of waves on a string is the square root of the force of tension over this thing called the mass per length. Okay, so if I have a length of string, it has a particular length and it also has a particular mass, it's the ratio of those two. In other words, it's a linear density of the string, the mass per length. Sometimes this mass per length is abbreviated using a mu. I know this is kind of unfortunate because we use the same symbol for the coefficient of friction, and don't worry, we'll use it for other things too, so lots of confusion for you guys. So again, we could rewrite this equation in this manner, but it means the same thing. And I think what you can see from this is that a greater tension will cause the waves to go faster. A more dense string, in other words, a heavier string, let's say we've got this string here and then we've got another string that for the same length has a lot more mass, you're going to get a slower wave speed for the big mass per length compared to the small mass per length. And it has to do with inertia.